So our next speaker is Alina Leuchtenberger. She's going to talk about learning from an artificial neural network in phylogenetics. Second.
Hello, yeah, thank you for the introduction. Yeah, so I will talk about a project I did together with Arndt van Heeselen. And let me start with the problem this network considers. And this problem is the problem of the Ferris and the Felsenstein tree. So both of these networks are four taxon trees. And both of these trees have a very short inner branch. And in addition, they have also two short external and two long external branches. And now, the Ferris tree, named after James Ferris, pairs the two long branches, and the Felsenstein tree, named after Joseph Felsenstein, always pairs a long and a short branch. And now, there is a problem, and the problem is that these trees are very difficult to be distinguished. And that was already observed in the early 90s. And the reason for this problem is also, for example, that these two taxa here, so the yellow and the green one, so the short length taxa, they are still the closest taxa according to evolutionary distance in the Felsenstein tree, even though they are not paired. And this is the reason why for an alignment evolved under Felsenstein tree, maximum parsimony infers a Ferris tree. While on the other hand, maximum likelihood sometimes tends to infer a Felsenstein tree for alignments evolved under Ferris trees. And now in the worst case, we have one alignment and maximum parsimony infers a Ferris tree and maximum likelihood infers a Felsenstein tree. And we would just not know what the correct tree is and which method is the correct one. And one example for this is the case of the Holometabula alignments, which were gathered in 1995 by Kamian and Crespi. And in this case, maximum parsimony places Strepsiptera together with flies, which is a Ferris tree. And maximum likelihood infers a tree where Strepsiptera and beetles are paired, which is a Felsenstein tree. And now this problem or this alignment and what the true tree is was discussed for a very long time. And so what we need is actually an answer to the question, how are alignments of Ferris and Felsenstein trees now different from each other? And the network I considered or I tried to learn from is the network Epsilon and N, which was trained to resolve this question. And Epsilon and N was trained on simulated data. So for this, we generated 270,000 Ferris and Felsenstein trees with different branch lengths. So we also consider sometimes trees with a long inner branch, just to have all branch length parameter combinations. And under those trees, we simulated in total 270 million alignments. We did this under the Jukes-Cantor model, so we assumed a very simple setup with equal base frequencies and equal substitution rates. And now, therefore, we have the alignments, which we can use as input to Epsilon and N, and we have the ground truth with the tree types due to this simulation. However, we don't use the alignment directly as input. Instead, we use side patterns. Sorry. And the side patterns that we only consider which sequences show now the same nucleotide in one site and which have different ones. So for example, here, the red sites have the side pattern where the first sequence has another nucleotide than the rest, and we denote this with this split writing, where the split denotes that the left and the right-hand side from the split have different nucleotides. So this would be then 1 split 2, 3, 4. And the orange side, for example, would be 4 split 1 to 3, as here the 4th position shows another nucleotide. Okay, and so with this, we can just extract the frequencies of the side pattern and have one vector of side pattern frequencies, which is used as input to the neural net. This neural network is a standard feed-forward neural network with one output value, which indicates if Ferris or Felsenstein tree is inferred. The training took place on this 270 million alignments I talked about, just with a normal gradient descent algorithm. Moreover, the network was evaluated on 2 million parameters, which were simulated independent of the training data. And on this evaluation data, the network achieves an accuracy of 87%. So it can indeed distinguish most Ferris and Felsenstein trees. However, this network, while it's a quite simple one, consists of 9 linear and 9 nonlinear functions and has 1.2 million parameters. And as I said, it's simple. There are networks with a lot more parameters or functions. Still, the decision process is not understandable at all this way. And therefore, what we did was we tried to simplify the network function as far as possible to gather in the end an explainable function. And we started by removing all but 2 interim layers, and we used a square function as activation function. We had the luck that it was still trainable, so in our case, this was not the problem. And with this, we got a function which is, in the end, a 4th degree polynomial. And the indeterminates of this 4th degree polynomial are all products of 4 side pattern frequencies. And the coefficients are just trained by gradient descent. And now it's important to note that this coefficient have nothing to do with the original parameters of f zone and n. They were trained independently, and one might think that network and polynomial have nothing to do with each other. However, they have in point of we would never have found this polynomial if we wouldn't have started from f zone and n, because we wouldn't have had the idea that a 4th polynomial could already solve our issue. However, it's still not very explainable. We see which parts of this function drive in the direction of Ferris or Felsenstein, but we still couldn't really understand why. Oops. And therefore, we went back to a property of alignments. And this property is that we can just write down an alignment, here just denoted by one side, in the order of red taxon, blue, green, yellow. However, this is not natural. You can also just write down it like blue, red, green, yellow. This wouldn't change the tree. The tree is still the very same tree. However, what is changed is the side, or better, the pattern of the side. So on the left-hand side, we have the first position being different. So 1 split 2, 3, 4. While on the right-hand side, we have now the second position being different. So 2 split 1, 3, 4. And in a similar manner, all reorderings of sequences change side pattern frequencies, or at least influence them. And what we can do now is that we could just formulate the whole thing as an equivalence class, as the sequence reorderings induce an equivalence relation on the indeterminates. And there we say just that 2 side pattern combinations are equivalent if and only if there exists a sequence reordering which transforms one combination into the other one on any so reordered alignments. And what does this mean? So let's look at this example of a combination of 4 side patterns. So if we switch here the 2nd and 4th position, then the first side pattern, this constant one, stays the same. If everything is the same, every nucleotide is the same at each position, it doesn't matter if I change the 2nd and 4th position. However, the 1, 2 split 3, 4 is changed. As previously, the 1st and 2nd position have the same nucleotide, and then due to the switch, now this previous 2nd position is now in the 4th position. we would have 1,4 split 2,3. 1 split 2,3,4 is again not changed. 2 and 4 have the same nucleotides, so switching them makes no difference. 2 split 1,3,4, on the other hand, switches to or is transformed to 4 split 1,2,3. Like this, we can basically transform all of these 6 combinations into each other, but just by using different sequence reorderings. And therefore, we call such a collection of combinations an equivalence class and denote it by one of its elements in square brackets. Okay, so there are 269 such equivalence classes with so if we consider combinations of 4 side patterns. And therefore, what we did next was to adapt our polynomial by replacing the 3060 products of side pattern frequencies with the 269 maxima of equivalence classes. And a maximum of an equivalence class here is computed by just collecting all combinations in one equivalence class. And then for each of those combinations, we get the corresponding frequencies of side patterns and multiply them. And then the maximum of this product is the maximum of the equivalence class. And so the result is a function which is linear in those maxima. Still not very explainable. So we have 269 terms now, which is nicer, but it's still not very nice. And therefore, we just iteratively removed indeterminates, retrained everything, and tried to figure out which maxima are now really important. And the result was that actually 6 equivalence classes seem to be very, very important. In the first 3, you see here E1, E2, and E3. And if we now just look at the combinations I used to represent them, we see that these elements are very similar to each other. So the first 3 side patterns are exactly the same. And the fourth one is in each case a single side pattern. So they have a quite similar structure. And actually the same applies for E4, E5, and E6. Also, they only vary in the 4th side pattern. And again, this 4th side pattern is in all cases a single side pattern. And therefore, it might not be as surprising that our, in the end, identified function is a rational function. And what we use actually are the quotients of the maxima of E2 and E1, E3 and E1, E5 and E4, and E6 and E4. And whenever Farfel discerner outputs now a positive value, we infer a Ferris tree, and for a negative value, we infer a Felsenstein tree. So let me give you a bit of an intuition why this thing works here. And for this, let's get a look on single and pair side pattern frequencies and when they are large. So with a single side pattern, I mean here all these patterns where only one sequence has a different nucleotide from the rest. So for example, 1 split 2, 3, 4 is the case that 2, 3, and 4 share the nucleotide and 1 has a different one. And this is most frequent if the branch of 1 is actually a long branch, because then we have then it's more likely that we have a mutation on this branch and that the rest has no mutation or mutation which cancel each other out. Or at least it's more likely than if this branch is rather short. For the pair side pattern frequencies, which are side patterns where 2 sequences have one nucleotide and the other 2 sequences have another nucleotide. So 1, 2 split 3, 4 means 1, 2 have the same nucleotide and 3, 4 have the same nucleotide. These are most frequent if 1 and 2 are paired and if the inner branch is rather long. Because if they are not paired, like here, and we would need multiple mutations to have the case that really 1, 2 have the same nucleotide and 3, 4 another. So this is definitely less likely than if we have them paired directly. And again, if the inner branch is long, it's more likely that we have a mutation there separating 1, 2 and 3, 4. And now, with this, we can take a look on far-field discerner, or better, this first difference. And to understand this, it's better to take a look on both of these quotients directly. And this we do by now just taking a look on side pattern frequency products, which are actually the thing which are the maxima of the equivalence classes, as the maxima of the equivalence classes were exactly the maxima of such side pattern frequency products. And now this blue one is actually the frequency of the constant side pattern, of the 1-3 split side pattern, and of the 2 split side pattern squared. And this is largest if 2 and 4 are paired, because then the 1-3 split 2-4 is large, and if 2 is long branched. And for this, we can find a Ferris tree, which fulfills those properties, and a Felsenstein tree. However, for this red one, where the last frequency is replaced with a frequency of 4 split, there we must have that 2 and 4 are paired, but 2 and 4 also need to be long branched. And therefore, we only can find a Ferris tree which fulfills this, as the Felsenstein tree never pairs the 2 long branches. And the yellow product is actually the converse. So here we have a 3 split pattern, so 2 and 3 need to be long branched, but 2 and 4 need to be paired. So we cannot find a Ferris tree like this, but a Felsenstein tree. And so in the end, at least for these 2 Ferris and Felsenstein trees, we know that this quotient, which considers the red side pattern divided by the blue, so the red side pattern product divided by the blue product, must be larger for the Ferris tree, and the right quotient must be larger for the Felsenstein tree. And therefore, this difference is positive for the Ferris tree here, but negative for the Felsenstein tree here. And this is correct for those Ferris and Felsenstein trees I just draw. However, we have a problem if the inner branch is very short, because then this doesn't hold anymore, as then the largest pair side pattern is not necessarily the pair side pattern pairing those taxa which are also paired in the tree. And therefore, we have this second part, which actually serves as a kind of correction value. Because this term basically has a large absolute value whenever the long branches are very, very long in comparison to the short branches. And the 09826 was actually fitted on the expected side pattern frequencies of Ferris and Felsenstein trees with different branch lengths in such a way that we didn't want to correct Ferris trees in the wrong direction, but we wanted to aid the wrong value for the Felsenstein trees. And in total, we got out that far-field discerner has a 98% accuracy on this expected side pattern frequencies, where F zone and N only achieved 91%. And it has still an 82% accuracy on the test data of F zone and N, whereas F zone and N itself achieved their 87%. And now let's go back to our original example of the holometabola alignments. So there we kind of had a problem in the beginning, or we thought we have, because these holometabola alignments didn't involve under a Jukes-Cantor model, or most likely they didn't. And so what we could do was we just evaluated far-field discerner on data simulated to reflect the holometabola alignments. And actually, far-field discerner was rather good there, as it achieved an accuracy of 85%, which is even more as the accuracy on the F zone and N test data. And so we applied far-field discerner to the holometabola alignments, and what we got out is actually a Felsenstein tree. So far-field discerner says basically that Strepsiptera is placed together with the beetles. And now the nice thing is that we can take a look why it infers this. And the first term actually is rather in the direction of Ferris tree, as the most frequent pair side pattern here is that which pairs Strepsiptera and flies. And so here, the reason for this inference is the correction term. And this indicates that we have indeed here a Felsenstein tree with a very, very short inner branch. And the nice thing, of course, is also that this is concordant with the current scientific view, as there were new alignments generated with higher quality and so on. And on those alignments, also a Felsenstein tree is reconstructed. And so let me come to the conclusion. So we identified an explainable function via the simplification of a neural network. And we could do this as we incorporated information on the structure of the data, or better, on the symmetries within the data. And the nice thing is that Farfeld-Soehner still distinguishes alignments stemming from Ferris and Felsenstein trees very well. And it does so by relating the maximal pair and single side pattern frequencies. And even better, as it also works fine on the holometabola sequences, it seems like this relationship between maximal pair and single side pattern frequencies, which is different for Ferris and Felsenstein trees, doesn't only hold for Jukes-Cantor data, but is more general. And of course, this simplification cannot just simply be applied to any neural network. But I think, especially if we have data with just such symmetries, we can sometimes try to use them and sometimes try to identify with them simpler functions which are still explainable. And thank you very much for your attention.